Okay. Good morning. It's good morning. It's a great pleasure to introduce Professor Klaus Strassmeier. I think he's very well known, but let me say a few words about his research career. He's the director of the Leibniz Astronomical Institute in Potsdam, a major research center near Berlin. He is an expert on cosmic magnetic fields, I think mainly in the stellar domain, but maybe also in other domains that I'm not so aware. He was also professor in Vienna, at the Vienna University, many years ago. For a long time, he has been director at the Potsdam Institute for Astronomy, more than 15 years now. And he's professor at the university also in Potsdam. Mm-hmm. Klaus has done a lot of research on stellar physics, and particularly concerned with the measurement of magnetic fields and surface inhomogeneities in stars. And he has been also a very active developer of state-of-the-art instrumentation for this scientific topic. And he's going to talk today about one of the best high dispersion instruments, high dispersion spectrographs that are running in the world, and currently located at the Large Binocular Telescope, where the Institute of Potsdam has right to carry out a number of observations, a number of nights per year. So this is a very interesting instrument. He has done many others in the past, but this is the last of your creatures. So we are eager to know more about how well it's performing, and thank you very much for coming to talk to us.
Thank you. I have this one. All right. It's always, and keep my introduction very short, of course. It's always a pleasure to be here, as I already chatted with some of the folks here. Whenever, even if you work here, it's vacation for me. It's minus 3 degrees in Potsdam right now, so short sleeves. What else are you asking for? So let me reflect my appreciation for the invitation here. It's actually my pleasure to come here. It's been a long haul here, building instruments on Teide, and running them is yet another thing. So, but now I think it's about something completely different. I want to introduce to you the Potsdam-Michel polarimetric and spectroscopic instrument. It's a high-resolution spectrograph and polarimeter, and it is the latest addition in the zoo of high-res spectrographs at the 8 to 10 meter classes. We have still Espresso coming up here from a consortium, which actually Spain is involved in, but it's not there yet. So PEPSI is at the 8.4 meter LBT, and it's indeed a big telescope. But be aware, because that's going to be confusing for you in my talk, it's two telescopes. Two 8.4 meter mirrors. From here to here it's 22 meters, and it can be used as a single mirror, and it actually uses the rotation to get the full visibility. So actually you can use it as a 22 meter telescope with just two apertures cut out of the mirror like this. So everything's big. So some of you recognize the Berlin downtown here. We use this sort of things to sell it at home, of course. I mean, be happy that we built in Arizona, because we would have never gotten a permit in Berlin, of course. So two mirrors, as I said, two 8.4 meter. These are the largest single mirrors ever made. All others that are slightly bigger, actually 10 meters, are segmented, as you know. When they're being used by PEPSI, which is just basically a flux collector. Sorry for the imaging folks here, in particular the IO people. It is actually an equivalent aperture of 11.8 meters. So, and that is the largest telescope in the world. And yes, it's big. You can walk around there and get lost. So we're occupying with the instrument a whole bunch of places on the telescope. Spectrograph is in the pier. The two units here we call permanently mounted fiber units, the permanent fiber units. The one side of the telescope is called, by the way, DX, the other one is called SX. Then we have a polarimeter on both sides, but it requires the straight-through symmetric foci. That's part of the polarimetric idea. If there's some solar people, I've seen one of it. They know what I'm talking about. So we have to exchange instruments for using the polarimetric version. Then there is a fiber feed, a 450-meter fiber cable underground to the Vatican telescope, which is nearby. And we have a solar telescope, a robotic solar telescope I'm going to show you soonish, that can also feed PEPSI during daytime. And of course, everything is connected with fibers. So we have a whole bunch of fibers there. Although it's a single object spectrograph, right? It's not a multi-object spectrograph, but we still have 90 fibers running up. So spectrograph, nice picture. It's basically a white pupil design and based on an R4 shell, the same than in UVs and in HARPS. It's used in a double-pass Litrov collimator. It's an F14 Maksutov, and with 3 different pairs of fibers with 3 different cores, we're obtaining 3 different resolutions. I come back to this maybe for the optical designer people or someone in here with a spectrograph. That 2D picture is much better for an overview. We feed in the light here, basically into the 4 optics and the image slicer units before you enter the spectrograph. Main collimator here, main collimator corrector lens, which is an off-axis Maksutov, grading, and then you split with the dichroic beam split in the blue and the red arm, again with their own transfer collimators. And then you have the cross dispersers here. Only one is shown. There are 3 of them. And finally, the optical cameras, blue and red, and the CCD at the end. The actual core technical components that made us reach the resolution, because the high resolution is the ultimate design issue. You need such a parallel collimated beam that the usual errors in grinding or in polishing off-axis parabola limit your parallelity of the beam, which it then limits your spot size on the optical cameras. In order to get that, we decided to go with Maksutov systems with high-performance correctors. So that is one point in reaching the high resolution. There's a lambda 80 surface precision on the spherical reflectors of those mirrors, so they contribute. The other one is the image slicer. The fiber core you would need, which projects this on the sky, is 1/10 of an arc second or something. So that's maybe for solar people, that's okay, but not for stellar thing. You lose all the light basically. So we've developed what we call a waveguide image slicer. Don't go into any detail really here, but it's basically a stack of glass plates separated with a waveguide, just a different refraction index, and then they're cut off by 45 degrees at the end and illuminated or silverized, and then the light gets in here and comes out in slices here. And there's 16 of those in PEPSI. Each fiber that comes down from the telescope has its own image slicer, and you don't have to move anything, so it's all fixed. That's also why we needed the Maksutov collimators. They have a wide field of view, so we don't have to move things. And of course, really stayed on the CCD. It's still too small. It's not two. Each arm has one of these 10K by 10K CCDs with 9 microns. The 9 microns also limit the spectral resolution sampling. We aimed for 8 microns, but that was a failure. Holographic mass precision was not good enough at those days we were doing those CCDs. But anyway, those are the 3 components that really made up PEPSI in its core. It's mounted on a bench, 6 by 2 meters. Here's a panoramic view. You know, your cell phone is doing everything for you, but then when you look at it, oops, where am I? So it is sort of pretty cramped. I don't explain you anything. It's just, here's the door. That's the size of the door. It's kind of full when everything is closed. You don't see it, of course, like this usually. It's in a pyrometric chamber. You see the walls here in the back. That's like a diver's chamber, right? When divers got out and they get into a pressure chamber, so that the exchange gets slowly into the barometric pressure, right? This is, has a constant, it's not a vacuum vessel naturally, but it keeps the environmental pressure within the chamber to 0.1 millibar or something in this order, at a 1 to 3 millikelvin temperature precision. So that's our Egyptian sarcophage, and that's basically when PEPSI is in operation, it looks like this. So, observing modes. If there are some observers in here that would ever want or dare to use PEPSI, of course, LBT is the main issue, but we have the two other telescopes feeding it. Those two are only usable in the ultra-high resolution mode, because it's a fiber core issue. And you don't want to observe the sun with low resolution, right? So there's two basic modes, integral light and polarized light. And as already said, for polarized light, we need an instrument exchange in the prime foci, in the straight-through Gregorian foci, as they're called, while the integral light mode is permanently available, and even under remote control from Potsdam. So 3 fiber pairs in the integral light enable a 2-pixel resolution of 250,000, a 4.2 pixel resolution of 130,000 with the 200 micrometer fiber, and a 12 pixel resolution, 12 pixel sampling resolution of 50,000 with the 300 micron fiber. It's 100 micron here. So on a sky, these apertures are then, you see 0.74 arc seconds, which is the median seeing of the side, 1.5, 2, and 2.3. So what we call our bad seeing fiber, still 50,000 resolution. So since we have two telescopes, and now it's the complicated part, under quote, you have 2 fibers per telescope, though, like my fingers. One finger is on the optical axis. It's 1 fiber pair. And the other one is 6 arc seconds away. So you have the choice of, well, of course, the target, or you can choose the target. So not push the wrong one here. And one have the sky in there, and the other you can use for simultaneous Fabry-Perot light from a Fabry-Perot étalon. So you get the wavelength calibration simultaneously on the chip. You don't read out the chip separately for your calibration frames. Now the spectral resolution, everything is laid out for here in our CCDs, yet 10 by 10K is still too small to do the whole thing in a fixed format, like HARPS or any our stellar spectrograph up there. So we need 3 exposures to get the full wavelength coverage 384 to 913. That is why there's 6 cross dispersers, 3 per arm, and these are the wavelengths that are being covered, and you can always use 2 simultaneously. Okay. And then we have a data reduction pipeline, because it's a nightmare, because once you see what the data product is, you're going to have fun with IREF, for example. Don't even try. So this is an invert. You see the 2 well-exposed spectra, which are the target fibers, and then adjacently each one a Fabry-Perot fringe pattern. If you zoom in, actually it's a little cheating. This is a zoom in to another spectrum, not of these, because here I have 4 thorium-argon shown. But I'm too honest sometimes. Anyway, what you see now is that 4 spectra per Echelle order. So we have 17 Echelle orders per exposure, per cross disperser. There are 6 of them, which makes close to 90, 92 Echelle orders. And each order is 4 spectra, and each spectrum is again sliced up with the image slicer. In this case, it has 7 slices if you count those. And each one is re-imaged, each slice is re-imaged on the CCD, and then electronically co-added. So, with this you can do spectra at very high resolution, and you're not losing too much in throughput. Because of course the image slicer, as a waveguide image slicer, has to go to glass. And glass is the enemy of astronomers, you know. Okay, so the first thing we've done, we of course looked at the bright targets where we know what they're doing, and we have something to compare with. Right? And one of the first stars, of course, Arcturus. Alpha Boo, we have now a spectrum alley in Potsdam on our campus. If we use one PEPSI spectrum and plot it, say in 10 angstroms per A4 page in white direction. Right? That's typically what you do when you want to look at spectra. The spectrum is 160 meters long. So we squeeze this into a little bit, so it's only 36 meters long from here to here. But this is Epsilon Eridani. Thomas is here just posing, of course. Anyway, so we have done, meanwhile, 50 of these stars in the very high resolution with really good signal to noise up to several thousand. And 50 of those spectral atlases are now published in those 3 papers this year in A&A. It includes all Northern Gaia benchmark stars, naturally all quite bright targets, but also Kepler 444, and most importantly, I spent some time on it, also the Sun. And feel free to download all of these spectra on our website. There's lots of things to be discovered in those data, even they are bright star and very well known. Here's a comparison, for example, on Arcturus. You see a section of, that's the G-band in Arcturus. The dots are the PEPSI spectrum, the line is the KPNO atlas. Don't try to find a difference on this scale, you're not going to find it. Here I've selected 3 wavelength regions. Again, now the dots are PEPSI, and the line here, you barely see it, is the KPNO atlas from Hinkle. But the ratio spectrum of those 2 is shown what is here at 1. Oops. So there is, for example, that's the calcium H line core. There is changes, but there were almost 20 years in between. There is changes in H alpha, as you can see very nicely. There's almost no change in lithium. Okay, fine. But notice those are the numbers. The Hinkle atlas was taken at Kitt Peak with the Kudafit telescope at a resolution 130 to 200,000 with signal to noise ratios from the optical cutoff peak and the red cutoff. And PEPSI had a little higher resolution. We had poorer signal to noise at the real cutoff because it's a fiber instrument, but we blow him away in signal to noise ratio everywhere else. But notice it took 50 nights for the Kitt Peak atlas. It takes 10 minutes. Just a sequence of 10 exposures, period. That's it. So this is Kepler 444. It's a very old star. It's actually a Methuselix, what we call it, 10 gigayears. It has five planets, 5 transiting planets, each actually below Earth's mass. So we've done a chemical analysis of. This is one deep spectrum from PEPSI. Actually, the bluest cross disperser is missing, but you can already see this is 4 hours of exposure now and co-added. So I don't want to read those numbers, but you get fairly good precisions. But an even better star to observe and compare the quality of your, or say, shortcomings of your instrument is the Sun. So we run a solar telescope on the kitchen balcony, completely robotic. It goes when the sun is up, it goes, points there and does nothing else all day long. Purpose was, of course, to monitor the PSF of the instrument. But scientifically, the idea is to monitor the sun as a star over its whole activity cycle. We use it in 250,000 mode and actually get the whole thing. Data rate is, of course, fierce. I mean, the nighttime is peanuts compared to the daytime. And of course, yeah, we've upgraded it in the meantime. Don't even start. It has to withstand weather, of course. LPT is at 3,140 meters height. And even if it's in the desert, it's ugly sometimes. So you have to have an instrument that sort of, for example, cables that don't worry about that too much. And here's the toughest test of all. First of all, the target, the sun. And then we look at the cores, in this case the K line, where the flux really drops all the way down to, you can see, below 10%. So, and what you see in this zoom in here is dots again, the PEPSI spectrum in the commissioning phase, and the line is the Courage Atlas taken in 1981. The Courage Atlas has a resolution of 470,000, and we have here 250,000 roughly. You can see this in the line depth, at some lines at least. It is strong as you don't, but notice in particular the sun was significantly less active in 2016 than it was in 28. So sun's activity is declining long term. So here's another example, another very, very important line for stellar physics, one of the neutral carbon lines, one of the few in the optics, the other one are all in this one band. It's actually this line here, but I'll show you the resolution here again. What is shown here again, let me just hit the key here. Yeah, is that line is a HARP spectrum of the sun. HARP says also, it's HARP's north, by the way. And a PEPSI spectrum is the dots again, and the Fourier transform atlas, in this case the Göttingen version, is at 670,000 is the deep line. So fitting well in there. Famous line is also lithium, of course. I usually ask my students, okay, point me to the lithium line and zoom in. Now, where is the lithium line, please? And if they don't go there blindly and point at the right light, you know, they're out. So test. Okay, it's that guy here. That is lithium, this little wiggle here. Observing lithium in the sun is awfully difficult. So this is a zoom in, and lithium alone on the sun is 4 lines. It's two isotopes, and each one is a duplet. So we obtain a full equivalent width of 4 milliangstroms. So for all this sort of feature is lithium. We have a non-detection of the isotope ratio, so we cannot detect 6 lithium on the sun with our instrument. But we get a very precise abundance, for example. And we do this all the very same way we do it on stars. Same optical train. And that's, I think, the big advantage. Because all the other instruments so far that measure lithium abundances are specialized instruments. They have either, like the FTSs, you have a disk sender spectrum, or some of them, when they're especially designed, you have a full disk spectrum. And some, of course, they can put the slit also, of course, into sunspots. And then you get a, 4,000 Kelvin sort of stellar spectrum. Anyway. This is just to summarize the solar observations, just to get an idea. That's the theoretical 2-pixel spectral resolution. And of course, notice the anamorphic magnification does not provide you a flat spectral resolution. So each shell order, which is shown here, is the separation between the arms, blue arm, red arm, has a certain gradient. That's inherent to all spectrographs, all shell spectrographs. Here's a single solar spectrum signal-to-noise ratio. Here's 1,000. And here you see already, these are the exposure times for those signal-to-noise ratios here. We have our sweet spot at around 700 nanometer. And frankly, at really 382 nanometers, 0. The fiber just doesn't give you anything anymore. Now, applying this to another star, of course, not to anyone, but we knew the guys. We've already now discovered 6 lithium in an evolved star, and there's quite some debate whether this can be true. According to all theories, 6 lithium should have been completely diluted, shouldn't be around. So I don't go into any sort of scientific details in each sort of spectrum I show you, because otherwise I'm going to talk here for ages. But it's been published this year, last year already. Point really is we're now thinking that this has to do with spallation processes in this very active subgiant. Basically, some of its flares contribute or produce 6 lithium. Completely different target, Nova Sagittarius, very bright nova. 2 years ago, 3 years ago, my goodness, time is fleeting, yeah. So we were following it with high resolution. Here's a full spectral range. Here's the spectrum of the sun for orientation. Sorry, I mean, at this wavelength range you can't orient really, but this is H alpha, beta. And here you zoom in the sodium D lines, for example. Here again the sun, the sodium D lines, those two features in the sun. And all you see here is the interstellar sodium. And the Nova Sag sodium is actually a P Cygni profile, which is an emission here and an absorption here. And same in, for example, O1, absorption, emission is a single line, the whole thing. But the idea here is each of these absorption features is a shell in the nova. So we've been following this from day 13 on, actually continuing, and we actually found lithium in it, in the shell. It's being produced, not been there before. It's being produced and it's fading. Here's the equivalent width, and we lost it already after day 21. It's 6 milliangstroms. So here's day 13, day 21, so time goes up, and here's the line itself, it's offset by roughly 500 kilometers per second, so it's actually in a shell that moves out of the star at 500 kilometers per second, and you see it with lithium, and it's decaying, and of course diluting. So this is neat. There's actually only one other nova where this has been seen so far, which is actually same year. Just to get you a little bit of a diversity type of spectrum, here you see an inverse P Cygni profile of a famous star, Dida-1 OREC, very young guy in a nebula embedded. But that's not really why I want to show you. I want to just show you the scale. I mean, this is mostly nebular, so it's not only from the photosphere of the star, it comes from the path along. It's really emission, circumstellar emission. But notice spectra are normalized at continuum. You actually see here the inverse P Cygni thing, absorption here. But notice it goes up to a height of 8. But observing another nova, like this one, nova VV9 Telphi, H alpha goes up to 300, which means there is no other light seen from that target than from the Balmer lines. If you have a guider on a telescope that excludes the Balmer lines for whatever reason, you don't see it. It's nothing there. It's quite amazing. So it's normalized to 1 again, as every spectrum here. And this is a 30-minute integration, signal to noise 200, 120,000. And at that scale, with 200 to 1, I mean, this is in density 200, so one dash is the noise level here. There's no noise visible whatsoever when you look at this. So if you think this is noise, completely wrong. This is all structured features. So this guy has zillions of shells emitting. And this is basically a radial cut through it in H alpha. You get also H beta, but that I don't show it. So another application is, for example, helium isotopes that are not so easy to observe because you have fairly faint stars. This is Feige 86, and it's basically a piece of cake to resolve that line separation. You get equivalent width of those two isotopes and get a ratio of 0.3, and that feeds back into the nuclear synthesis and basically is in agreement with the standard model of cosmological nuclear synthesis. Other isotope ratios, most importantly carbon isotope 1213, which is more or less an age indicator. We have done another really bright star, but be aware, very bright but very difficult, strangely enough. It's a binary with two giants of same mass, so you have to disentangle the two spectra. So what you see is only the primary star anymore, primary at those wavelengths. If you go with 500 nanometer, the other star is the primary, and that completely dilutes the spectrum. But anyway, here's a wavelength region where you can compute the 12cn and 13cn ratios, just very simply by comparing, because that's dominated by that feature and that's dominated by that feature. So you zoom in here. So you get you do line synthesis here for those two features, as I just mentioned, you get a ratio of 18 plus minus 2, which is quite surprising. We're still a little worrying, but the previous value, but however 30 years old, is 27 plus minus 4, and it was never an agreement with stellar evolution tracks. So maybe that is, and that would fit perfect actually, but there's so many issues. I just want to mention that just if you observe bright stars, that doesn't mean things become trivial. So, not a fainter star, Tabby star, you may have heard about. It's the one that fades and rises in Kepler all the time, and some folks had even thought there's some space station encircling it, and that makes the light dimming and blah blah. Here's a single spectrum, or actually it's 4 spectra of the sodium D line. It's not the doublet. I just zoomed in into a single, the D1 line, and you see there's at least 1, 2, 3, 4 lines here from that single star. So the ISM in that direction is significantly structured. I would say there is at least 4 clouds. That's not the ultra high resolution. So, but it basically shows, hey, wait a second, you may have an alien structure there, fine, but there's also some structured ISM in between. So another similar science is done with Zeta Ophiuchi. It's an O star, it's an O subgiant. It's only used as a light source in the background, and you observe its light that's transmitting to us and see how it's going to get absorbed. So since it's an O star, so this is the full PEPSI spectrum here, the high resolution. You can already see the sodium D lines. Boom, they go down to 0. The star is black and sodium D. It's all absorbed. You see some other features here in the blue, but that's not what we're after. We're after the molecular lines as well as the lithium line in the ISM. Zoom in here. This is a strong, comparably strong helium line. And since this is a non-radial pulsator, you see it very nicely structured with this non-radial pulsation features. But what we're after are these sort of what other people would think are, you know, data reduction or some noise issues. No. If you zoom in here, you actually see the lithium doublet, and do an analysis on it. You find it actually with equivalent width, with one cloud and 4 spectrum lines fit, because the 6 and 7 isotope plus each one a doublet. You get equivalent width of the full line of 0.4 milliangstroms and 0.6 on the stronger one, with an error on this order. That's 250,000 spectral resolution and initial signal to noise of 1700. And you can see you're still limited by noise, as always. That's our nature here. Completely different again. We're looking at the Io moon of Jupiter. This time using the Vatican telescope. Don't need a 10 meter to observe a 5th magnitude star. 5.7 magnitude is Io or something in the order. Problem is with the LPT pointing so close to Jupiter, because it blows up the wavefront sensors. So 130,000 mode, 30-minute exposure, signal to noise. This is a spectrum with the same configuration of the Sun. These are the other 3 Galilean moons, and then there's a time series of Io, and we just were lucky and caught a launch of a sodium jet on the surface. Notice that these spectra are plotted in the heliocentric frame. You see this is the sodium D, both D lines, they're aligned. But of course the sodium jet goes with Io. And it took basically less than a day to launch it from 6 to 50 Jupiter radius. So it's a very dynamic phenomenon. We're not experts in this, but it was just fun. Actually, we have a program coming up now in May when Jupiter is back again. We're observing an eclipse of Io, and it's cooling. So we can actually observe it while it enters the shadow. And then you observe molecules, or we should observe molecules being formed due to its sudden lowering of the temperature. This has been proposed and actually there's evidence for it from HSD, photometry however, all I'm trying to say is you can do even planetary stuff with a spectrograph on a nighttime telescope, not just spacecrafts, right? All the time, of course. Can't observe Mercury as beautifully as Bepi Colombo, but anyway, oops, what was that? Was one too much? So, one of the actual reasons we built PEPSI was we were wanting to do Doppler imaging of not only fainter stars, but also of slower and slower rotating stars, which means the more and more solar-like. We're not there with PEPSI yet. I think we really need the ELT and the Iris spectra for that. But here is the young sun in the sky. It's still 10 times faster rotating than the sun. So its omega is 10 times higher. You see a series of spectral line profiles here from bottom up is time. These are average profiles. Dots are the observations. The lines are the inversion fits. These are averaged spectral lines, averaged with a singular value decomposition procedure. I don't go into any detail here. But basically, these are averaged from all the spectral lines in the spectrum. And the signal to noise that you see here and that the inversion code sees is 15,000. It's not 1,500, that would be already pretty nice. Now it's 15,000, because we use on the order of 3,000 spectral lines and actually remove the noise on each one, because it's the same type of noise up to a certain point, and then co-add them. So what we found is a Doppler image for this star. This is temperature. And we saw a very nicely isolated spot. And we believe that with this spot, if we zoom in, we see for the first time at least evidence for a penumbra like it's been commonly seen on the sun. We're not there yet, I would say, but the evidence, if you compare to a sunspot, isolated sunspot, which is this picture, which is also related to a temperature profile, which is the black line here, and our spot, which is the histogrammic sort of line, you see that the penumbra temperature change is very well matched with this feature, but we do not grab the full line chord. So the intensity ratio on that star, by the way, Ica Draconis, you still don't have the spatial resolution basically to the Doppler effect in the V-sin-I as compared to a direct image. So I think we see we have seen penumbras all along, but we've never seen the real umbra. So some of you may have now already asked, now what about radio velocities? We're not in a vacuum chamber, surely, but we're still doing pretty good, I would say. This is 8 hours of solar monitoring with this robotic solar telescope, one spectra after the other. It's roughly 300 spectra, and 2 cross dispersers. Only 1 cross disperser is shown. And actually, you get a nice 5-minute peak. So you actually already detect the P-mode oscillation from this disk average. So we're always talking about the sun as a star. So we get the whole thing into the fiber. Right? It's like a star, right? So you plot this versus the period that we got here. This is what you get. It's an external sigma of 1.2 meters per second for that one day, but the amplitude of the 5-minute oscillation disk average is actually 47 centimeters per second. So I think that is the limit for the spectrograph. No signal-to-noise issue. That long a time coverage is almost impossible in nighttime. But so it may get better because this is already 2 years old. But that's the order. The other side of the coin, you go to nighttime to really faint targets. We've done this guy, TRAPPIST-1, actually the G planet. Observe a transit of it in last November. Now TRAPPIST-1 is a V magnitude of 18.8, but an I magnitude of 14. It's an M6 dwarf star with 5 planets, 2 inhabitable zones. This is 4 hours of monitoring. Here we have meters per second again. This is the eclipse time, mid-eclipse. Our RMS of the whole thing with 10-minute integrations is 5 meters a second for that length in time. We were after observing the Rosita-McLaughlin effect. We see an inverse thing, but frankly not significant. Basically just driven by those 2 points, and that's not. So I think we are at the limit. That's it. But frankly, espresso will have a hard time. So other planet stuff. Other planet stuff. Cal 21. It's an A star, and you see the transiting planet just in the profile. Very nice. That's been published. A very interesting thing we haven't published yet, but are in the process. We have detected potassium in this very bright and very famous planet host star. Here's the potassium line, by the way, in a single CD6 cross disperser spectrum. Transit was October last year's resolution, 24 exposures, bang, 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 bang. So what we did was basically using, here's a zoom of the potassium line, observing the flux, measuring the flux here and in 2 continuum bands and building the ratio and then plot it over time. And then you see the eclipse starts here, eclipse ends here, meaning it's a beautiful 10 sigma detection of potassium. And that's the first time actually in this particular planet. Here's my so far highlight, sort of. It's actually now a true spectrum of an exoplanet. What I've shown you before was just an indirect flux ratio related. Here you actually have Kelt 9b, which is a hot super Jupiter, so that's the easiest target. So, but we built a spectrum from the star inside transit, when the planet was in transit, divided by the star outside planet transit. Just like you normalize. You basically divide the star away. Right? So, zoom into, you can't read anything here. This is cross disperser 3, you see H beta here. Resolution is now 50,000, so low resolution mode. And you can zoom into other lines here. You see there's quite different. And even if you further zoom in here, you see even more weaker lines. And if I zoom actually into this section here, those 3 guys, it's actually the magnesium 1 triplet. And notice now the intensity scale here. Even on the sun, we were able, and it's getting pretty tough at the 1% level of the continuum. Here we're at the 0.1% level. Here's a better plot maybe of the magnesium triplet. There's other blends. But basically this is 0.1% here. So, you can measure the equivalent width of all these lines in the spectrum, plot it over time. This is then your transit light curve, basically in spectral lines. And you see that, oops, it goes back into emission. Eclipse start, eclipse end, egress, egress phase. So there ought to be, and it's not symmetric either, so there ought to be some structure in the atmosphere of that particular planet. And it's a hot super Jupiter, and it's likely being blown away by its host star. H alpha already gives you an indication. It's a dynamic spectrum. H alpha, it's not homogeneous. It has structure in there. So we're entering now the regime where we do spectroscopy of planets. I think that's kind of good. I skipped this. This is a Mercury transit. We've done this. Here's Mercury, by the way. We've done solar eclipses with the solar telescope and spectra like this. I skipped this. So this is the last eclipse. You measure, for example, sodium D lines again, measure the bisector in it, and then as a function of time. Convective blue shift, as you see beautifully here. But what you can do now, because, let me just go briefly back here, yeah. Because you obscure once the Doppler red shifted and once the Doppler blue shifted part, you can actually say where your bisector is on a star, from where it comes from. So you can now choose a particular point in the bisect and then extract the radial velocities there. And if you do it, say, for the central part, you get the radial velocity. You can do it from another part, and you get the velocity at that point of line formation. So, and for the radial, where the vertical velocity I is identical to the radial velocity, that's where you should see the Rosetta-McLaughlin effect of the moon on the sun. And that's nothing else. It's like this here. Using the convective velocities. Love it. Polarimeters, we have 2 polarimeters. Don't have any time anymore, so just let me skip through. Here's the telescope focus, dual channel polarimeter like we do on the sun, all Stokes vector. Here it's during mounting. Here's the polarimeter, the acquisition guiding wavefront sensing unit, and the mounting flange, the image derotator on one side of the telescope. Here it's mounted on the scope. First light spectrum, a very bright star, and there's also a Hubble spectrum at similar resolution. If you compare those two, in Stokes I, we get signal to noise 912 minutes. The Hubble spectrum signal to noise 420, which is beautiful in twice as long a time. But this is really what I want to show you. That's the PEPSI null spectrum multiplied by 5, just so you see it. Red is the Harp's null spectrum, and the PEPSI null spectrum is just flat. So it just means nothing else. We have not seen any crosstalk between circular and linear yet. So here's the first application that's basically going to be rounding up with a little movie later. We have done in commissioning time a time series of, I think, 14 spectra of IAPEG, which is a spotted star. Here's Stokes I overplotted. You see the changes in the line profiles. And here is Stokes V, 1 spectrum per night, just for visibility. And you see the null spectrum. These are multiplied by 10 compared to here, and this one multiplied by 50 compared to here. And you see the complex line profile variation, even by eye. This has not been common, say, with espadons or harps, that you see those by eye. You have to apply a line co-addition techniques in order to see all of this. So what we get is a Doppler image. Now, in this case, a temperature Doppler image. First, that's the quote easy part from Stokes I. Its resolution is still unprecedented because we have higher spectral resolution. And V's and I chopped off by the spectral resolution determines your spatial resolution. But what we found here is this. Look at this. There's a very cool and a very hot spot adjacent to each other. This one and this one. And if you now go to the Stokes V inversion, basically we're not doing this separately, we're doing this simultaneously, but we can show you it separately. Then it looks like this, and you can already see field strength in Gauss, that those two features are very dominant, and the bright feature that we've reconstructed from Stokes I has different polarity than the other one. So what we believe to see here is nothing else than the flux tube that is connecting each other, the two polarities. So if you compare this, you can see that these are really co-aligned. So those spots, those two at least, most likely, it's not proved probably, but they're most likely not formed by convective suppression, but are formed by shock fronts heating from top down. And we don't have an analog of that on the sun. So if I do a force-free extrapolation on these features, and there's two of them. One restricts closed loops to above 2 stellar radii, which is the left, and the one is for shorter than or less height than 2 stellar radii. Otherwise, it's completely a mess if you plot them together. And you see, for example, that these different polarities always connect. And here, these two strong ones are really a huge, gigantic flux loop, more like what we see in trace movies of the solar corona. but actually visible in the photosphere of that star. So that's my summary. PEPSI is a spectrograph polarimeter at the LBT. We use it, of course, in binocular mode, which means both mirrors simultaneously. And by the way, maybe just as a gimmick, you can point the two telescopes 2 arc minutes off. So we can observe a visual binary, one star with the one side and the other star, on the same detector, the same spectrograph. I haven't done that yet, but that's a gimmick. Anyway, so 2 fibers per telescope makes 4 spectra per shell order, per exposure. We have that wavelength coverage, which is basically the full optical. And I already mentioned the low resolution mode with 12 pixel sampling, and up to the high resolution mode with 2 pixel sampling. The polarimeter has only a single fiber pair, 200 micrometers core diameter, and therefore only a single spectral resolution. Of course, you can always bin in dispersion direction. But you're not gaining too much. But so the instrument is stabilized, not comparable to HARPS and not comparable to Espresso either, but it's stabilized at least so that the short term is definitively better than 1 meter per second. The long term is likely more on the order of 5 meters per second, where the word long term has to be defined. We are not there for that long yet, but say 1 year long. The winter-summer change is the killer, or it's the limiting thing probably. So this is to be determined yet. Big advantages we have whenever the telescope, the LPT is busy, we have access to the Vatican. We have a deal with those guys sitting in Tucson. We're using currently 50 nights per year with the Vatican. It's 450 meters of fiber. So if you see a blue photon, welcome it. Otherwise, so the blue arm is basically not usable, frankly. So SDI, the Solar Disk Integrated Telescope, is being used daily. So we're taking daily spectra of the sun. Commissioning is done, and meanwhile we're observing for other LPT partners in remote control from Potsdam in integral light mode, nothing else. So I appreciate your time. Thank you very much.
Thank you so much. I'm sure there are questions for Klaus. Yes.
Hi. So thank you for the talk. I wonder if you are monitoring the sun for radial velocity variations. I mean, to try to, for example, to see the signal detection from Jupiter or something like that.
No, we don't actually, but the data is there.
Okay. No, because I think it should be interesting if you are monitoring daily this.
I remember Molaro et al. had done something already with ARPS North, right? No, they've been using Vesta, I think, for solar velocity monitoring when basically perturbation by the sun, perturbation of the Earth by the moon, and then you observe the sun and then you see it. Yeah, it's funny. I mean, we all correct our spectra to pericentric velocities, right?
Yeah, of course.
They are uncertain at that level.
Yeah, so this, I wonder maybe for the monitoring of the spectrograph you are doing this kind of monitoring.
Yeah.
So I
No,
wonder
good,
if you see
good,
something.
good point. Yeah.
Any other question?
Have you tried on any stable star the mode in which you can shine light for the calibration lamp from the Fabry Perot at the same time as you do the star observations? Does it help with the precision? Can you push it?
I think on a single observation it doesn't, because the spectrograph is stable for the short term, so that doesn't really help. And the fringe width, I mean, we have roughly 100 fringes over one width of the CCD, over one shell order. the only thing it helps if you have consequent time series. And actually we are monitoring the Fabry-Perot stability because it's drifting with a thorium argon. As I think all of the people do. But you depend on the 0 point of your thorium argon. If your thorium argon tube, fades away, your 0 point is gone. Yeah, the laser comp is for the full wavelength range, first of all, not available, and secondly, for the amount of time we have on the LPT, just too expensive.
And have you found a limit in the signal to noise that you can achieve?
Oh yeah.
Because of the
Signal to noise
ability or things like that.
That's a good. Yeah, my goodness, that's a really a long story. First, we thought it's the fibers limit the signal to noise, modal noise issues, this sort of thing. But it's actually the flat field. So we're using now what we call a supermaster flat, which is basically taken all the time. So we're taking, I don't know, it involves roughly 10,000 flats taken over 14 days. And then you build one flat field out of that. And then you keep on going, just doing this. And you use that whenever you take a spectrum, you choose the one nearest in time. That supermaster flat was actually needed. It's not because of signal to noise, but the CCDs themselves have what we called fixed pattern noise, which comes, it's an awfully long story. I mean, some people may know it, and it's an inherent production issue. You see the clamps where they were holed in the wafer production. You see back reflections within the roughly 200 atomic sublayers at certain wavelengths, at others not. And this, at that level, it's called fixed, sure, but that doesn't mean that the amplitude is also fixed, right? So we have to monitor this. And when it comes down to reaching signal-to-noise ratio of 8,000, which is the maximum we had so far reached, I mean, you can still continue, you reach higher, 15,000 we had in the flat fields, 8,000 on a target, I mean, 8,000 on the sun. It's 100 images, 100 spectra at the end. There we basically reach a sort of a limit. So, but I think that's okay with 8,000.
Can you comment what is the magnitude limit for magnetic field detection?
The bandwidth.
What's the magnitude limit?
Oh, magnitude limit. Holy, I don't know yet. Basically, we're finishing the commissioning in the coming May. So we have had our first commissioning run in October last year when we were heading off. I can tell you one thing for sure, which actually was an incident in the first commissioning run. The ADC on one side was not completely aligned with the ADC on the other side of the two telescopes, and it caused a differential effect. Basically, the linear field vectors, you align, the polarimeter to the north-south direction to a very high precision, was a little off. It was always the same, but it was a little off. So basically, your field vectors, when you do the Poincaré sphere, right, did you get to the 0 point, were not really 3, and they had not 90 degrees in between. So they're just 89 or something. And that definitively, well, not only limited, screwed it up in linear. Stokes V was not affected, for example. It had not seen. So if you measure magnetic field from Stokes V in this case, that would be okay. But I cannot really quote you a limiting number. But we plan to do M67, solar-like stars in M67, in one of the upcoming runs. Only in Stokes V. Stokes, the linear components may be too faint. It takes too much time.
Are you running the magnetic field measurement also on the solar measurements?
No, not yet, I should say. We're right now actually rebuilding the SDI telescope and adding a polarimeter on it, so that we do it full disk full vector polarimeter. Then yes.
Is there any other question?
So what do you think the prospects are for seeing the evolution of magnetic fields, and then also things like reconnection?
Yeah. Oh, yeah. Well, reconnection is a little bit of a separate issue, but the first issue is, of course, formally magnetic flux is a conserved quantity, and we observe on the sun that it is not the case. So you have to go basically in larger steps in time. So there may be phases in stellar evolution that just don't care about the magnetic flux, because it's being like, and maybe even the solar, where the sun is in right now, we may not be caring about it. But we may very much care about it when the sun was at the age, say, of the Pleiades. So I want to basically resolve solar-like stars, in particular in M67, with CDI techniques, and then determine not only the field density for the features in the surface, but also their area, to produce a real physical magnetic flux, and then set this in evolutionary connection, and need an age sequence of clusters and see where it really makes any difference when you compare the two tracks. Then YREC is the code we input magnetic flux, but it's a parameterized quantity. It's not like you run a global dynamo and that as a function of time. That's not doable. But that's the idea. Sorry, long.
Is there any last question? If not, we thank the speaker again.
Thank you.
And just let you know that there is scientific coffee at the cafeteria now, if you want to go.